Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing our study of Chapter 5 on thermodynamic processes and cycles, and we are looking at the vapor compression refrigeration cycle, and specifically we are looking at how we can select the choice of refrigerant for our refrigeration cycle. There are many chemicals that we might choose as a refrigerant. The NIST Chemistry Web Book has thermodynamic tables for the most common refrigerants, which I also have included diagrams here. But we have, for instance, refrigerant 134A, which operates into pressures up to about, TC is around 4 megapascals. We have our 422A, which similar pressure, okay. Our 134A, again, also a similar pressure. And then we have R22, which, what's the critical point on that one? It looks to me like it's about 60 bar, 50 bar. And then we have here refrigerant 12, which is what most people call Freon, okay? And it also operates up to a similar kind of value, 4,000 kilopascals, 4 megapascals. I'm going to take a break here and remind you of what some of these things really are, because we call these by names that are not chemically descriptive. R12, its chemical name is difluoromethane. If you were to draw it, right, it's going to look like a methane molecule, that little tetrahedron shape, okay, with 2 fluorines attached and 2 chlorines attached. Now, these are called chlorofluorocarbons. They will release that chlorine when they decompose. Problem is, chlorine reacts with the ozone in the upper atmosphere, which produces oxygen, which ends up breaking down the ozone layer and is an early contributor to global warming. The CFCs were banned in 1987 and largely replaced by hydrofluorocarbons. No more chlorine, but they still had the fluorine there. Now, these HFCs still are greenhouse gases and do contribute to global warming, and so they are in the process of being phased out, and they are being replaced with simpler hydrocarbons where possible. Now, typically what you're going to find is that if you're looking at old automotive air conditioners, originally they were designed to work with R12, the Freon that we mentioned. More recently, since 1987, R134A, and as people became concerned with global warming, these have been replaced with either R1234YF, which is tetrafluoropropene, or carbon dioxide. Yep, there's a good use for carbon dioxide. And in refrigerators such as you probably have in your home, R22 is the old style, R410A is its replacement, but more recently we're using isobutane, which is also known as R600A, or ammonia, okay? Now, the R12 and R22, those were destroying the ozone layer, and so they were phased out in 1987. R134A and R410A are still global warming. They are greenhouse gases, and so they're still being phased out today. These are more recent choices, but they all have their own risks and benefits. In particular, for refrigeration, consider that isobutane is quite flammable and ammonia is quite poisonous. So which one of those do you want in your house? Right, you see the issues here. One of the things that we are going to also want to do is we are going to want to avoid air leaking into the system because it will cause our refrigerator to malfunction. And so therefore we always want to have vapor pressures of the refrigerant at the evaporator temperature. So our lowest pressure needs to be greater than atmospheric pressure. And then we want the high pressure to not be too high because that's going to cost us a lot more in the initial equipment cost, and it's going to cause more operating expenses, and it's more dangerous if something were to fail dramatically. We also want to think through things about safety and the environment, right? Is the material hazardous? Like I say, do I want something flammable or poisonous in my house? And then when it ultimately does end up leaking into the atmosphere, because no matter how we try to contain it, some will, what damage is that going to do? So there are, serious environmental concerns. But we also have to think practically. So is the phase change that we need even possible? Is it going to phase change to solids? Because solids don't flow very well through a cyclic system. How high is my pressure? That's going to affect the equipment cost. And it's the fluid expensive. I'm going to have to make sure that it's fully charged with my refrigerant. And so is that going to be expensive? And is the material corrosive? Is it going to damage my equipment and start just eroding and causing system damage over time? So these are some of the primary concerns. We're going to look at an example. We want to look at a vapor compression refrigerator that has an evaporator operating at negative 20 degrees C and a condenser operating at 40 degrees C. Okay, so I'm needing it to get to negative 20, and I'm going to be releasing heat at 40 degrees C. That's going to be my TH. The evaporator, I'm just going to have it produce a saturated vapor, and the condenser is going to produce a saturated liquid. And I want to look at the coefficient of performance for a variety of working fluids. Now, I have started with a data table here. So I've given that T2 is negative 20, T4 is 40. The quality at state 2 is 1. The quality at state 4 is 0. And at state 3, it's going to somehow be a superheated vapor. I don't know exactly any more than that. We have all of our usual assumptions. And I'm going to ask you to go through and do these calculations on your own as far as you're able to. If you do this problem for water, methane, and nitrogen, I want you to pause the video and look up as much of this information as you can. And then when you get stuck, come back and join the video again. All right, what did you find? Well, what I saw is that for water, this forms a solid at negative 20 degrees C. I can't pump a solid or compress a solid. A solid's not going to flow through my valve, so this will not work. What about the methane? When you tried looking that one up, and the nitrogen, you've exceeded the critical point. You are at temperatures above the critical point, and so two phases are not possible. If you can't form two phases, then the evaporator and the condenser are not going to be able to perform. And so therefore, this is not going to be working fluids that we can use. So these three won't work. Let's try refrigerant 134A, 410A, and ammonia. Again, I would like you to pause the video and try working this for refrigerant 134A, 410A, and ammonia. You can find data tables online or wherever. You can use the graphs in the book, etc. Welcome back. Let's look at what I found for first refrigerant 134A. Using pressure in kilopascals, states 1 and 2 are at 133.7 kilopascals. States 3 and 4 are at 1,017 kilopascals. The quality at state 1 was 0.39, and the enthalpies for states 1 through 4 in order 256.54, 386.08, 428.1, and 256.54. Doing this, the coefficient of performance was H2 minus H1 over H3 minus H2, 129.54 over 42.02, or a coefficient of performance of 3.08. What about for our 410A? For refrigerant 410A, the temperatures range from -20 to 80.5, so a much higher high temperature. And the pressures are also higher, 399.6 megapascals. Oh, I think those are kilopascals also. And 2420.7 kilopascals, so 2.4 megapascals. The quality at state 1 is about the same, 0.39. And the enthalpies are listed here, 124.09, 271.89, 329.48, and 124.09, leaving us with a coefficient of performance of 2.55. So we have dropped the coefficient of performance with this refrigerant. And finally, what about ammonia? What I found was the pressures range from 190.2 kilopascals to 1,555 kilopascals. The high temperature is 135, much higher. I didn't find the quality. I didn't look that up, sorry. Enthalpy is 371.43, 1418, 1737, 371.43, all much larger values of the enthalpy. And our coefficient of performance is 3.28. So now let's consider what we should actually choose. So I've summarized our findings. For our refrigerants in order 134A, 410A, and ammonia, the minimum pressures we found were 133.7, 399.6, and 190.2. So all of them are higher than atmospheric pressure, which is certainly one of our criterion. This one, 399.6, is a lot higher. It seems like maybe a bad idea. It's not the end of the world, but we could probably go with something a little lower there and still be safe. Our maximum pressure, okay, very alarming now. So we're at 1 megapascal for 134A and 1.5 for ammonia and almost 2.5 for R410A. So that pressure is very high compared to the others. So this would make that, maybe not such a great choice. But let's look at the other issues. So we have coefficient of performance. My best coefficient of performance was for ammonia with 3.28. My worst was R410A at 2.55. The amount of heat transfer per kilogram in the condenser for the 134A is 129.5, R410A 147.8, not a lot of difference there, but ammonia was 1046.6. Now this is much higher. This is a really good thing because that means I will require less of the ammonia in order to make it work. So a higher Q on a per kilogram basis means that I don't need to have as much fluid in order to make the system work. Now I also looked these up, the SDS sheets on each of these chemicals, and just the basic easiest information. So the flammability rating for R410 and ammonia is a 1, which means it can catch fire, but it's not likely to be a serious danger. Reactivity, R134A, is a 1. Health is kind of the big one. R134A is a 1. I'm usually pretty happy with 1s and 0s in my house. R410A is a 2. Ammonia is a 3. Okay? These are going to be really problematic to have in your home. And yet, these, are considered good choices in many cases. So, when you're making a choice, you need to decide, are you doing this in an industrial setting? In an industrial setting, the fact that I have materials that maybe need extra containment, that's a little bit more reasonable in a factory setting than it is in a home. And the higher pressures are going to be, pros and cons depending on my setting. And so therefore, you have to kind of take all of these things. There isn't any one of these that it's like, oh, this is clearly the winner. All of them have some good features and some bad features, and you make the choice that is appropriate for your setting. So this is going to conclude our look at basic vapor compression refrigeration. In our next 2 videos, we're going to look at other ways that we cool materials using other refrigeration and then also liquefaction. Thank you very much for your time.